We shall now resume, and for this we'll, as we said before in the first part, we'll divide everything in here by delta t and send delta t to 0, and also in here. So the first term here should converge to the partial derivative with respect to t, while in here, in this part here, we are going to have two terms. One which is going to be the term which corresponds to k of z, and the other corresponding to the transition from t to t plus delta t. It's going to be the term for the transition, for the instantaneous transition from the point y to the point z. So this is what we are going to do next. So for this, so the first term is going to become dp dt equals, so dp dt equals, so one term is going to be the transition, so this is the limit as delta t, goes to 0 of this probability of x of t to be at z plus dz and being alive, minus the probability of f of t, for x of t to be located at y plus dy and being alive, divided by delta t, plus, and we have the remainder term, which is minus k z and t, multiplied by this probability of x of t plus z plus dz and being alive. So in the limit, we'll get dp dt, and this we know that what it is. This is exactly the Fokker-Planck operator. This is the Fokker-Planck operator, as we have seen before, because this is a transition from z to x, so from y to z at infinitesimal time, minus kz, so this is supposed to be independent here of time, multiplied by p. So this is the equation satisfied by this. P is here the survival probability. So this is the survival probability. So the classical expression for L is, as we have seen in previous classes, this is L of P, which is sigma transpose divided by 2. This is d dxi, this is ij, this is dp dxj, and this has to be summed over I and j, minus d dxi, the drift, which is b of I multiplied by p, and this is the sum over I. Right, and so there is another method to go slowly about it. It's to use the path integral, which I want to discuss very briefly. So the path integral method is to use between t and t plus delta t, that the survival probability density function satisfied the probability to switch to y at t plus delta t is, so this is written in dimension 1 here, but this can be written in n dimension. This is infinitesimal operator, I mean the propagator, for the delta t exponential, so the switch from x to y minus b of x delta t, so this is divided by 4 delta t d, so this is squared, and now this has to be multiplied by the survival probability, which is 1 minus k of x multiplied by delta t multiplied by p of x n time t, and this has to be integrated over all dx. And so the Fokker-Planck equation can be written by looking at to study this as delta t goes to 0 by doing an expansion in here, so that p of x here can be expanded, for example using a variable which is square root delta t xi, square root xi square root delta t. Alright, so this I will not go into this. Now let's continue to discuss the solution. There is a stochastic solution for this equation, stochastic expression, and the stochastic expression for this survival. So this equation is called the survival probability density function, PDF. Survival probability density function, and this can be written using a stochastic expression, and this is called the Feynman-Katz formula. So the equation is the following. So again, so now let's discuss. This is the Feynman-Katz. Feynman-Katz expression for the survival probability density function. So if P is solution of dP dt equals L of P minus K of X P, it is possible to find the solution of the equation on the following form. This is Px of t. So if the initial this initial value for p is f of x, so then this is the expectation. It is given by the expectation for all trajectories f. So now this is there are two expressions. One is for the forward and the other is for the backward operator. So I will give now the expression for the backward operator. So when we have here L star, so for the L star operator, which becomes here with a minus, then this is f of x of t, and this is exponential from integral from t to capital T of the killing rate. So in the following expression with a minus, so this will become with a plus, so then it becomes plus k of s, and this is ds, condition that x of t equals x. And this is not the limit in 0 but in t. This is in the limit of t going to capital T. So this is one expression for this Fokker-Planck equation, and this I will refer to the previous class for the derivation. So what is interesting in here is that there is this stochastic expression for the solution of the probability density function, but this expression is not usually useful, it's not practical. So this expression is not really practical for calculation, for the computation, for asymptotic calculation. So right now I'm going to discuss how it is possible to calculate from these previous expressions. So first of all, we are now going to discuss what happens if we would like to estimate the probability, for example, to arrive alive. So suppose there is a a particle starting at x, and what's the probability that the particle arrive here at the boundary alive. So in principle, if at each moment of time the particle is killed with the rate k of x, it is surviving with this rate, 1 minus k of x delta t. So in principle, to answer this question, we would say that this can be answered using the probability density function, but if we discretize all the points where the particle is going, let's say x of n, then the probability to escape alive should be in principle the average over all, over all possibilities, which is x1 delta t. This is the product of all steps x2 up to delta t, and then we have to multiply by 1 minus k of xn delta t, and this is the probability to arrive alive, and this has to be taken over, so I will do quote unquote, this has to be done for all possible trajectories. So to make this notion clear, we'll see that we'll have to use this probability density function, and in particular this probability to escape alive. This is, first of all, we can look at what's the probability that the particle is alive at time t. The particle is alive at time t in the domain. This is precisely the integration of the survival probability density function over the entire domain d of x omega. So now, what is the probability? What is the probability that the particle escape alive from the domain? So for this we have to define there's a killing time. This is the first time that the particle is killed. That is such that the particle is killed. And then there is arrival time, which is the first time that the particle is at the boundary, arrived to the boundary of the domain d omega, and this is omega. So what we are interested in is the probability that the time to arrive is less than the time to be killed. And this can answer the question of the probability to escape alive. So if we start with the probability density function for the survival, which is solution of dp dt equals L of p minus kp, if we integrate from 0 to infinity this equation and integrate over the domain omega, so as we do this integration in here, what do we get? So the first term, integration from 0 to infinity, will give us p of x time infinity minus px of 0, and now we have to integrate dx over the domain. So the probability that the particles escape is 1, so at infinity this should be 0, and at 0 for sure the particle is in the domain, so this is precisely minus 1. Now this, the second term, is just the integration from 0 to infinity, integration over the domain omega of k of x p x and t dx dt. And now the first term can be, as we have seen before in the class, this can be written in a divergence form. It's minus divergence of the probability flux j. So if we integrate over omega as this, by Gauss theorem, this is just the flux over the domain ds. Now, so this is integration from 0 to infinity of integration over the domain j dot normal because this is j dot normal ds over d omega. And because of the minus which subsists here, we have a minus. So this now can be exactly reinterpreted in terms of probability. This is plus the 1 equals 2 term, and now we can identify that the flux here, this is precisely the probability of escaping alive. So what we obtain from this equation that we're going to rewrite here is 1 equals the integration from 0 to infinity of the flux j dot n ds dt plus integration of k of x multiplied by px of t, and this is dx dt. So this is integration of omega, integration from 0 to infinity. The probability to arrive alive is precisely this term, which is the flux, the density flux over the boundary, and because everything sums to 1, the other one is precisely the other one, which is this one, integration from 0 to infinity, integration of omega of px of t dx dt. So this answers, if we know how to calculate these quantities, this answers the probability to escape alive or the probability to be killed. So there is now the possibility to derive mean first passage time equations for the conditional time. So I propose let's do this now, and then we'll discuss some applications. So conditional mean first passage time, which is what is the time, let's say, to escape at A, condition that indeed you escape alive and you started, let's say, at position Y. How to calculate this? So the mean first passage time by definition is the integration from 0 to infinity of d dt of the probability of tau A less than t, condition that tau A is less than tau k, and the particle started at Y. Now, this probability, tau A less than t, condition on tau A less than tau k, this can be written using Bayes' law as the probability of tau A less than t and tau A is less than tau k multiplied by the probability and tau A is less than tau k, which is precisely what we calculated. This is what we've calculated in here. And the probability that tau A is less than t condition on this can be written by, this is exactly the flux, the probability flux. So the particle here has escaped alive before time t. This is exactly the integration from 0 to t of the density of flux j of s ds, where j of s is the integration over d omega of the flux j of n ds dsy. So this shows that this can be precisely computed as a solution of element that are solution of the Fokker-Planck equation, the survival Fokker-Planck equation. This is ds divided by, so the probability that this is probability that tau A is less than tau k. So with this, it is now possible to express the mean first passage time, and so I leave this as an exercise. This is just by integrating by parts. It is possible to show that the mean first passage time, so let's call it conditional mean first passage time, E tau condition the tau less than tau k. This is the integration from 0 to infinity of s j of s, and then again divided by this probability then tau a is less than tau k. Now this can be expressed, such a probability, and this can be expressed in terms of solution of a partial differential equation. So let's look at this specifically. We can write, because the probability, let's say for example probability of tau k less than tau a can be written as, by changing the order of integration, this is integration over omega, integration over t of k of x, pt x and y, and this is dx. Now if we call p tilde of y, this is the integration, which is really the Green's function, integration from 0 to infinity of pt on x and y dt. Then for example it is solution of L of p minus kp equals, so this is the integration for 0 to infinity, so this is p tilde. It is obtained by integrating from 0 to infinity the Fokker-Planck equation. This is dp dt. So at p infinity this is 0, so this is minus p initial. This is the initial, so this we are left with solving an elliptic, this is an elliptic PDE to be solved with boundary condition. And so the boundary condition can be given, for example, as reflecting or absorbing, so px equal pt of x equals 0 on the omega, or we can have mixed boundary, which is j dot n, the flux, equals 0 on the reflecting part of the boundary. So now probability then tau a is less than tau k is 1 minus integration over omega of p tilde of y dy. Multiplied by k of y, which can be approximated, for example, in the case of the narrow escape formula. Using narrow escape analysis, it is possible to get an expression for, let's say, the probability that a particle arrive alive to a small pore. So for example, so now this is an application. Suppose you have small patches here. So those are the absorbing window. So those are the absorbing windows. Then it is possible to estimate the probability to arrive alive to one of these windows while the particle is reflected everywhere else. So this can be done by doing analysis on this equation. So I will leave this for those who are interested as an exercise. So basically, for example, for pure diffusion, the equation reduces to d Laplacian p minus k p tilde equals, let's say, minus the initial density with the boundary condition. So those are here the boundary conditions plus boundary conditions, and using the methodology. So I will refer to the following paper. So the probability to arrive alive for a particle to arrive alive to one of n to one of n nuclear, small nuclear pore So this is precisely 1 divided by 1 plus 1 divided by 4n dA integration of k dx over the domain omega. So this can be the analysis of this can be found in, so this is an approximation. The analysis can be found in the following paper in the Holcman Journal of Statistical Physics in 2007. How to do such analysis. Alright, so basically by going in that direction, it is possible to formulate, so this is what we've just discussed here. The probability to arrive alive is 1 minus the probability to be killed. This is solution of this equation, and the approximation can be obtained this way. This is exactly what we have done here, where A here is the radius or the size of the n equivalent small hole. And here we have plotted the analytical result for P of n as a function of the killing rate k. And you have here simulations versus analysis, analytical formula. This analytical formula versus the simulations. And what was interesting is that it is possible to predict, in this case, with the theory and simulated value, what's the probability for a particle to arrive to a small nuclear pore. So you can just plug the numbers about the radius of a cell. So this is the radius r of a cell. Delta is the nucleus. D is the diffusion coefficient, as n is a number of small hole, and r here, this is the radius of the small holes. This is going to be the end for this for the discussion of the killing into the stochastic equation. So I would like to finish by saying this. In the previous classes, we have discussed the Feynman-Katz formula, which we have seen here is not very useful. However, the asymptotic using the narrow escape can be used to derive asymptotic formula for the probability that the particle arrives alive. Stochastic particles arrives alive. And so this has application, as we have discussed the application in virus trafficking, or it can be in any kind of trafficking, such as polymer, DNA, polymer trafficking. So that's it for this introduction. Possibly in the next class we'll discuss how the killing can also be applied in other in other applications. We'll do that next.